Yeah, I'm that guy. Let me bother you all with this. Yeah, I also want to thank the organizers for this incredible conference and these great talks until now. So I'm Lluis Galbany, I'm a Funded Fellow at the University of Chile, and I'm going to talk about Integral Field Spectroscopy and environmental supernova studies. A work I did with a number of people, shown here. I don't know if you can check the bold names. These are actually here in the conference. It's nice to talk after Cristina because she has already mentioned a lot of things, all the introduction, so I will go fast here. The best method to constrain so to connect the supernova observable properties to the progenitor scenarios or for candidates is to check in these photon images, go to these archival images and check what was there. But there are just a few objects like this. So if you want to have statistical samples, an approach is to study the environment. This has been proved useful both in core collapse supernova studies and type 1a supernova studies. For core collapse to prove stellar evolution models and progenitors, or for type 1a's to introduce second order corrections in the light curve standardization. So far, people have been doing imaging of the galaxies, the fiber spectroscopy at the center, or putting the same kind of things but at the supernova location. Integral field spectroscopy gets all this information in one shot. I will talk about two different spectrographs, IFUs, integral field units. One is a fiber bundle, another an imager slicer. This is not, what I just said is not fully true, because in fiber bundles, as you see, there are few spaces that do not overlap with fibers, so you have to do 2 or 3 pointings for each galaxy. But anyway, it's more than having 3,000 slits there. With imager slicers, you cover the 100% of the field in one shot. Part of the work I'm going to present is in the framework of the Khalifa survey, which was because it finished in April this year. It was a survey of more than 600 galaxies, nearby galaxies, that were selected from SDSS year 7, based basically on the diameter of the galaxy. From this selection, there were like almost 1,000 galaxies from which we observed randomly, as I said, more than 600 galaxies. We used the PMAS spectrograph, IFU, mounted to the 3.5 meters telescope at Carlalto in Almeria, Spain, using 2 different setups, mid resolution and high resolution, covering the whole optical range, with the spatial resolution of 1 times 1 arc second. The field of view is 1 arc minute, 1 square arc minute, and with this configuration you get almost 3,000 spectra per galaxy. All the data is already public for the 670 galaxies in 3 data releases. What I basically did is to feed each individual spectrum, 100 million spectra, with this single stellar population models from Charlotte 2007, which is an update from Charlotte 3, using Starlight, code that looks for the best combination of these models. And once you feed the data, you can see here in black the spectrum and the red the feed. When you subtract that, the stellar component, you have the pure gas component. With this, you can measure the rotation and several things, and all the properties you can imagine with projected distances. This is an example of a galaxy. This is how H alpha flux map, 2D map looks like. But you can do this with whatever line. This is a rotational field map for the H alpha shift. This was the gas. This is the stars. From the feed to the stars, you can also see how the stars are moving. You can do this from the gas. This is the average age of the population at each position. These line ratios, you can start doing things like that. For example, 2D PPT diagrams. That's my own. Yeah, you can check where the AGN emission is coming from. Extinction maps from Balmer lines or also from the stellar field. Metallicities, star formation rates, whatever you can do normally expect. I will talk with this about these two papers. This is about correlations between supernova type and star formation in general, star forming regions. At that time, in 2014, we had 81 galaxies with 95 supernovae, which I divided in three groups, type 2s, including two L, P, and Ms. For us, L and P doesn't make difference. Then 1BCs and 2Bs and 1As. This year, we published the whole set of Khalifa host galaxies, which are 115 with 132. I will show you after that we are trying to improve these with new observations in order to speak with 1B, 1C, and 2Bs, and getting out the 2Ns from here. No division between 2Bs and 2Ns. So first thing is relation with star formation. Even when we checked, we collapsed the cube and we measured a real total spectrum of the galaxy, and we checked that the star formation of all galaxies were, or host galaxies with different supernova types were quite similar. When you look at the position of the supernova, 1BCs tend to have higher values than type 2s and 1H. Sorry. This dotted line is 1H in star forming regions, and here you add the integrals. Even only the star forming regions, the star forming galaxies, sorry, are you see this sequence. This result is reinforced looking at these three different parameters. This is the average stellar age, the percent of the young stellar populations, meaning lower than 200 megayears, and the H-alpha equivalent width. In solid lines, you see what happened at the supernova location, so lower ages in both collapse supernova types, higher percentage of young stellar populations, and higher H-alpha equivalent widths. So this H-alpha equivalent width, the meaning of this parameter is how important is the young population compared to the old population. It's not just like this, that is H-alpha emission of the approximate star formation. You can also see probably the dotted lines. And another interesting result, these dotted lines represent the total distributions. So when you collapse the cube. One important thing is when you compare the red and the black line with solid lines with the dotted lines, you see that they, at supernova locations, the values are higher. But when you compare the blue lines, they seem to be similar, not statistically significant. And this is good for supernova cosmology when you have the global property and you want to use that for standardizing and for checking what's happening at the supernova position. Another similar result that reinforced the previous is when you have the H-alpha emission maps, you can select these H-alpha H2 plans, not H2 regions because the resolution is not that good. And then you measure the distance from the supernova to the center of the H2 plan. When you do that, you see this sequence that also highlights that the 1BCs are closer to where things are happening than the type 2 electrons. We have some millimeter data from the H survey, which observes 175 Khalifa galaxies. We got 23 of those in our sample. And when you see what's happening with the CO emission and those positions, you see that these parameters can be related to extinction. It's the Coulomb density of H neutral hydrogen. You see that at 1BC positions you have higher values, and when you compare that to the AB from Balmer lines at the supernova positions, this is something that I think Maxito showed the first day. Maybe he's in so core collapse have local extinction higher than 1BC. On the other hand, metallicities, we can produce this two-dimensional map of metallicity and the metallicity gradients. The important thing here is that for 30% for a significant fraction of galaxies, we see these degrees in the center, not only with these 115 galaxies I have in my sample, but with the whole Khalifa sample, this percentage is similar. So when it's claimed that 1BCs are occurring high metallicity environments because they are closer to the center, one has to consider this bias. These are the results from the Khalifa sample plus all the data I know so far that are local measurements. I produced these two plots, splitting in targeted searches and targeted searches. The most important thing here is when you compare maybe the green line with the red line. These are 1Cs and these are 2Bs in a targeted sample. There is a significant difference between those, so metallicity is playing a role between 1Cs and 1Bs. In targeted samples, Supernova, sorry, there is a difference, not that significant, but here when you take out this bias of targeted samples, you see that difference. I didn't say that we are currently working on increasing the sample by size by a factor of 2 with new observations that are not part of the Khalifa. IFS studies, I presented this high field of view data, low spatial resolution, 1 times 1 minus 1 times 1 seconds. Hanin has been working a lot on, has 2 papers on small field of view, 6 times 6 seconds, but with high spatial resolution, 0.2 seconds. But news, the new, it's 2 years ago, but this quite new IFS, the BLT in Chile, is giving both things, large field of view and high spatial resolution. We started with Joe. Joe is the PI of this project. I'm using survey. Check the poster. It's in front of the toilet. It's next to Skylar's poster. So this is work using Muse for compiling a sample of nearby galaxies. As an example, you can see here an H-alpha map of NGC 2906 from Khalifa. So this is the resolution we have been working so far, and this is the same map, H-alpha emission from Muse. So we are working as an open collaboration. We have a platform where you just send us an abstract, say what you want to do, and we have already more than 200 galaxies. This is the team. This is the people who is involved. The board, where we're calling the board. Joe is the PI. Myself and Thomas. In blue, you see the Chilean-based investigators. Eric is in green because he was Chilean at some point. And I think in bold, they put people who is here. Yeah, well, whatever. It's people from Supernova and Galaxy communities, so it's good because we are doing the Supernova stuff. Other people is doing the Galaxy stuff. This is a pilot study we have been doing the last year. We sent a proposal for the science verification of the instrument. We got 6 galaxies. We, for the first time, did this kind of plot that we already seen many times. But this instead is H2 region statistics. So each point here is an H2 region, and the symbol represents the H2 region, the parent H2 region of the supernova. So we did a similar segmentation and just measured the parameters of this at this position. We expect to do that with the whole samples. Well, here I just show a few maps, H-alpha maps, rotational velocity map. This is H-alpha equivalent width. This is average age, and this is metallicity and the gradient. We see how it go up, and that's great. So, in summary, IFS has proved to be a powerful technique for looking constraints and studying supernova environments. Large field of view allows for proper comparison between local and total. High spatial resolution is too fast. It's needed for. Wait, I'm going to start again. So high spatial, large field of view is good for comparing total and local. High spatial resolution is good to check what's happening very close to the supernova, and Muse is providing both things. And we already have more than 200 galaxies. So that's, thank you.
So questions? In the meantime, Luis can brief.
I don't have to have formal talk.
Okay, let's thanks Luis again.